Imagine a computer that doesn't just try one solution at a time, but explores every possible path at once. That's not science fiction, that's quantum computing, a new kind of machine that uses the strangest rules in physics to solve problems that would take ordinary computers millions of years. So, how do they actually work? Why are tech giants betting billions on them? And what makes them so mind-bendingly powerful? Let's break it down. Every device you've ever used, from the first calculator to your smartphone, relies on classical bits, the simple language of ones and zeros. They flip between these two states to represent everything: photos, text, even this video. It's brilliant, but it scales poorly. When problems get really complex, like simulating molecules, optimizing global shipping routes, or cracking modern encryption, traditional computers run out of road. They'd need exponential time to check every possibility one by one. That's where quantum mechanics changes the game. Quantum computers use qubits instead of bits. A bit can be 0 or 1, but a qubit can be 0 and 1 at the same time. A strange property called superposition. You can picture it like a spinning coin, heads, tails, or both until it's observed. One qubit doesn't seem like much, but when you link many together, their combined states explode exponentially. While 10 classical bits can represent one of 1024 combinations, 10 qubits can represent all 1024 simultaneously. That's the secret: parallelism built into physics itself. But there's more. Entanglement. Entangled qubits share a hidden connection. Changing one instantly affects the others, even across distance. This correlation lets quantum computers perform massively coordinated calculations where outcomes depend on many variables at once. Superposition gives power, entanglement gives control. Together, they make quantum computing unlike anything we've built before. Here's the trick. Quantum computers don't try every answer and print them all out. They use quantum interference to make wrong answers cancel and right answers amplify. It's like waves in a pond. Some overlap and vanish. Others reinforce each other into a clear signal. Algorithms like Shor's algorithm use this interference to factor huge numbers, breaking encryption schemes that protect our data. Others, like Grover's algorithm, speed up searching through enormous data sets. Instead of brute force, quantum computers let physics do the heavy lifting. There's one massive problem. Quantum states are fragile. The moment a qubit interacts with the outside world, its delicate superposition collapses. This is called decoherence, and it happens faster than you can blink. Quantum computers have to operate in near-absolute zero environments, shielded from every vibration, photon, and magnetic ripple. That's why you see those futuristic silver cylinders in labs. Those are dilution refrigerators keeping qubits colder than outer space. And even then, errors creep in. That's why scientists are building quantum error correction, encoding information across many qubits so the loss of one doesn't destroy the calculation. There's no single way to build a quantum computer yet. IBM and Google use superconducting qubits, tiny circuits where currents flow with zero resistance. IonQ and Honeywell use trapped ions, individual atoms held in place by electric fields and manipulated with lasers. Others are experimenting with photonic qubits, light particles, topological qubits, or even silicon spins, each chasing the same goal: stability, scalability, and coherence. Every approach has trade-offs. Some are faster, others more stable, but no one's built the perfect system yet. So what can quantum computers actually do right now? Mostly research and simulation. They can model small molecules for drug discovery, help design new materials, or explore quantum chemistry that classical machines can't simulate exactly. Eventually, they could revolutionize logistics, AI optimization, financial modeling, and cryptography. When people talk about quantum advantage, that's the point where a quantum computer does something no classical machine can. We've seen hints of it already, but we're still in the early days. Quantum computing isn't about making your laptop faster. It's about solving entire categories of problems that were impossible before. It's still experimental, fragile, and incredibly complex, but progress is accelerating fast. Each new breakthrough, better qubits, smarter algorithms, more stable systems, brings us closer to a future where quantum computing becomes a real tool, not just a lab curiosity. The next revolution in computing won't come from more transistors. It'll come from mastering the weirdness of reality itself. Would you trust a computer that thinks in probabilities, not certainties? Because that's what's coming, and it might just reshape how we understand information, intelligence, and the universe itself. If you enjoy this type of content, subscribe and comment below which part you found the most fascinating.